Welcome everybody, my name is Aaron Barrera and I am a product marketing engineer for the Texas Instruments motor drives team. In this video, I will be talking about protection features provided in motor drivers. Let's begin. Today, I will talk about how protection features work to detect unsafe conditions. Then, I will discuss in detail 4 of the protection features found on the majority of TI's motor drivers, as well as briefly mention specific protection circuits found on other motor drivers. TI's motor drivers are equipped with a variety of smart protection circuits that protect the motor and system when unsafe conditions occur. Many of these circuits use comparators that trip if a threshold voltage is exceeded for a particular condition. If that occurs within a period of time, the driver will automatically disable the power MOSFETs to protect both the motor and FETs. Protection features vary by the motor type, family, and interface the driver supports. For instance, a simple brushed DC motor driver with an integrated H-bridge may only have the basic protection features including undervoltage, overcurrent, and overtemperature. A more complex device, like a brushed DC or brushless DC gate driver, can require advanced protection features such as open load detection, short to battery or ground diagnostics, VGS monitoring, and gate drive monitoring. Finally, some devices have a hardware interface, whereas other devices have a serial peripheral interface called SPI. SPI devices provide more information about what fault occurred and give engineers flexibility on how they want the driver to respond in a fault condition, which I will cover in more detail on the next slide. The pin central to any fault generated on a motor driver is called end fault, found on many hardware and SPI devices. This pin is used to report that a fault condition has occurred. There are many differences between hardware and SPI configurations in regards to fault reporting and fault handling. In hardware devices, many operating parameters are set by default, and there is no indication of which fault has occurred besides end fault being driven low. Often the device will automatically restart and enable the drivers after the fault condition is removed. In SPI devices, the user has the advantage of knowing exactly what type of fault has occurred and configuring what actions are to be taken by the MCU. If a fault occurs, a fault bit is set in the SPI register according to the type of fault detected. Then based on the SPI configuration, the device responds to handle the fault. The user can allow the device to recover automatically, clear the fault bit or enable a reset pulse once the fault has been removed, generate a report only, or take no action. In some devices, there is no configurability for a fault because the device automatically handles it, so the MCU must clear the fault bit to resume normal operation. Now let's talk about 4 of the most common protection features found in motor drivers. The first protection feature to talk about is supply undervoltage lockout, or UVLO. Undervoltage lockout occurs if motor supply voltage Vm falls lower than the UVLO falling threshold voltage. If that happens, the MOSFETs and charge pump are disabled automatically and a fault is generated by driving the end fault pin low. Once the motor voltage is higher than the UVLO rising threshold, the gate drivers are re-enabled, end fault is driven high, and the device will continue to operate normally. An undervoltage hysteresis is implemented in order to ensure undervoltage occurs beyond the supply noise floor and the device will not repeatedly shut on and off. The next protection circuit is charge pump undervoltage, or CPUV. Any motor driver that has a high side NMOS power MOSFET may also include an integrated charge pump. This generated charge pump voltage enhances the high side gate driver, so if the charge pump voltage is not sufficient, it cannot be assured that the NMOS is being turned on. When the charge pump voltage falls lower than the CPUV threshold voltage at any point, the MOSFETs are disabled and a fault is generated by driving end fault low. Once the charge pump voltage is higher than the charge pump undervoltage threshold, the CPUV fault is removed, end fault returns high, and the device will continue to operate normally. The third and potentially most important feature on motor drivers is overcurrent protection. When driving a motor, Power MOSFETs are used to control the PWM switching from the gate drivers. If there is a short to VM, ground, or a shoot-through condition occurs, then overcurrent conditions must be monitored to prevent the FETs, motor, or motor driver from failing or being damaged. Therefore, overcurrent protection, or OCP, is integrated in a variety of methods depending on the device features. OCP occurs if the output current exceeds the overcurrent threshold IOCP. When OCP occurs, the device has a fast-acting analog current limit which reduces the output current to a manageable level in the case of a hard short. If the reduced current exceeds the threshold after a deglitch time period, all of the MOSFETs will be disabled and end fault will be driven low. Some hardware devices automatically retry to enable the driver after the fault has been removed, whereas SPI devices have configurable modes to decide what actions happen after the overcurrent fault detection. For example, as shown on the right, the DRV8873Q1 is an integrated H-bridge driver with a SPI interface. The short to VM at the OUT2 node creates a high current spike through the low side FET that exceeds the overcurrent threshold, triggering an OCP fault. The OCP fault bits will be set, end fault will be driven low, and actions are taken depending on the OCP configuration mode. For devices with external MOSFETs, the voltage difference between the drain and source pins of that MOSFET, called VDS, can be compared to an internal threshold voltage. If VDS is greater than that threshold, then a VDS overcurrent fault will trigger. When driving a half bridge, only one FET should be turned on at a time. In that case, VDS monitoring only happens on FETs that are on. Let's analyze VDS of the high side FET. If the high side FET is on and low side FET is off, VDS on the high side will be equal to RDS on times the FET current. RDS on is typically in the range of milliohms, so VDS will be a small amount of voltage of about less than 1 volt. Suppose the output is shorted to ground. Now, when the high side FET is on, VDS is essentially equal to VM, and a large amount of current will sink through the FET. The VDS exceeds the VDS overcurrent protection threshold, and the device will generate an OCP fault. The MOSFETs will be disabled, and end fault will be driven low. Likewise, for devices with current shunt amplifiers, or CSAs, OCP will occur if the voltage difference of an external shunt resistor is higher than the threshold voltage of the CSA. When the low side FET is on, Vsense will be equal to the sense current times the sense resistance. Likewise, the sense resistance is typically in the range of milliohms, so Vsense will be a small voltage of about less than 1 volt. If a voltage higher than the threshold is detected, an OCP fault will be triggered. The MOSFETs will be disabled, and end fault will be driven low. The final main protective feature found in all TI motor drivers is thermal protection. Die temperatures are monitored through an internal temperature sensor and monitors the temperature in internal logic. Suppose the load current is 2 amps for a long amount of time. The die temperature T sub j will continually increase as the driver operates. If the temperature of the die exceeds the thermal warning trip point, an over-temperature warning, or OTW, occurs. The device will continue to function and a report is generated in the SPI register. It is important to note that over-temperature warning is not in all TI motor drivers. If the temperature continues to rise and exceeds the trip point of thermal shutdown, then the over-temperature shutdown mode occurs, or OTSD. The MOSFETs are disabled, the charge pump is disabled, and end fault is driven low. If it is a SPI device, then a fault bit will be latched high. When the die temperature is less than the thermal warning temperature minus the thermal hysteresis temperature, the device will automatically retry to resume normal operation. This wide thermal hysteresis allows for the device to return to a cooler temperature before resuming normal operation again. There are many other specific protection features that TI motor drivers incorporate into their devices, depending on the device, family, and interface. Overvoltage protection occurs when the motor voltage is higher than the system voltage rating. This will protect from overpowering the motor and unexpected behavior in the outputs. Gate driver faults indicate whether the gate drive signals are appropriately changing during the period of time it takes for PWM switching. By not detecting a change in a period of time, this can detect output shorts on the gate drive pins. Open load detection is a feature that sends a fault when the load is disconnected from the output stages of the MOSFETs. Offline short to battery and short to ground diagnostics are available on devices to detect shorts on external components before the motor starts to spin. Dead time is a feature implemented on TI's smart gate drive architecture. The motor driver continually turns on and off the FETs in an output phase, so both FETs must be off to avoid shoot-through current conditions. To implement this, digital dead time is automatically inserted to protect the integrity of the FETs, gate driver, and the motor. Furthermore, Smart Gate Drive can also protect the MOSFETs from accidental turn-ons through intelligent monitoring and driver actions. To find out more motor driver technical resources and search products, visit ti.com/motordrivers. Thank you for watching.